Hello, welcome to your lesson on binomial distribution and finding expected values and variance for binomial distribution. Alright, for the first part of this video, let's just listen. Don't worry about writing anything. We'll get to the notes portion a little bit later. Okay, let's remember our key statistics. So way back when we learned statistics, we learned about measures of spread, and the two common ones there were variance and standard deviation. Those tell us how spread out a set of data is. We also learned about measures of central tendency, which tell us about where is the center of a data set, and the ones we looked at were mean, median, and mode. Now let's look at some data sets. For example, we have this data set here. That data set has a low variance. We can see that there's not much spread, and variance is a measure of spread. So this isn't spread out very much, therefore low variance. We can also say it has a low standard deviation. Look at the bottom data set in the light color. That is spread out quite a bit, so we say that's high variance or high standard deviation. In the middle here, we can say we have the mean or the average. Both these data sets, the light and the dark, have the same mean. We can see the mean is at the center of the distribution. Okay, here's some more data sets. Tell me about Project C. Okay, Project C has a low mean and a low variance or low spread. How about Project D and E? Well, Project D, we can see, has the same mean as Project C, but a higher variance or higher spread than C, whereas Project E has the highest mean of all three, and also the highest spread. We can see it's most spread out, so highest variance or standard deviation. Okay, so here's another example of that. We have, this is showing weather, and let's see, here's average weather, here's cold, here's hot, and we have the previous climate here, and previously the climate had a mean right here and kind of a big spread, and then it says the new climate is this curve, so you can see the climate changed from this curve to this curve. It moved to the right. So what happened to climate under this situation? Well, the spread is still the same, it looks like, but now under the new climate there's more hot weather because it all shifted to the right, so the average is higher, and then there's more in the hot zone here. Let's compare that. So that was an increase in mean, right? The mean went up, but the variance stayed the same, the spread was the same. Now let's compare to one where we see an increase in variance. So now we have the previous climate, which is the same as this one above. It's this curve here. And then the new climate is this bottom curve that's spread out more. So that bottom curve, the new climate now has more spread. So under this new climate situation, we have more cold weather, more hot weather, because it's spread out more. Not more, sorry. There's a lower colder temperatures, higher hotter temperatures, but the mean stays the same. The mean temperature stays the same. Alright, so that's again, increasing mean, and here's increasing variance. Now let's take some notes. You've been provided a notes page. Let's use that to take some notes on expected values and variance. So we've been talking about binomial distribution lately. For binomial distribution, the mean value is called the expected value. So in this binomial distribution, there's always a mean or average, but we call it the expected value. To find this mean, we're going to use this formula here. So expected value of a random variable x is equal to the number of trials in binomial distribution. Remember, this represents number of trials times the probability of a success. We're going to use that formula now. So you have this situation. You flip a fair coin 8 times. What is the expected number of heads? Well, you might be able to kind of hypothesize this. Not hypothesize. You might be able to, just using logic, give the answer here. But let's see if the formula produces that same answer. So let's try. First, before solving it using the formula, let's write the binomial distribution. And remember that we said random variable x is distributed binomially with number of trials 8, because we're doing 8 coin flips, and the probability of a head is 0.5. So again, number of trials and probability. Now using this formula, what do you get? Well, expected value is 8 times 0.5, and we get 4. And that might be what you were thinking in the beginning. When you flip a fair coin, if everything goes according to theory, half of them will be heads, half will be tails. So we expect 4 heads. Okay, try part B. Okay, first, we talked about the egg roulette situation, and we had 3 trials, and there was 2 out of 5 eggs were raw eggs. So that's the probability of getting a raw egg. So now, what is the expected number of raw eggs? So if you ran this experiment, what is the average number of raw eggs we would have? And we can see a raw egg is 2 out of 5. If that was 2.5 out of 5, in other words, 50% of the eggs were raw, then we could say, well, we would expect 1.5 of the eggs to be raw, because that's exactly halfway. But this is probabilities a little bit less than 50% of eggs are raw. So we're going to have an expected value of raw eggs to be below 1.5. Again, 1.5 would be exactly half of 3. But we expect less than that because the chance of getting a raw egg is a little bit less. So let's see what the formula gives us. Multiply those, and we find out that 1.2 eggs are expected to be raw. Try the third one there, part C. Okay, in C, so we have a biased dice 30 times. We have a binomial distribution with 12 throws, because it tells us that here. And the probability of getting, let's see, number of sixes. Okay, so the number of sixes is said to be 8 out of the 30. So 8 out of the 30 is the probability of getting a 6. So that probability was established through an experiment, and we often do that. Sometimes we have a theoretical probability. In this case, we have a probability that's developed through experimentation, and then we use that probability to take us further as we do more trials, right? So we ran the experiment, got the probability, and now we're doing 12 tosses and seeing what we expect to get. So multiply those, and you get a value of 3.2. So you're expected to get 3.26s in the next 12 throws. Okay, so that was expectation or mean, and now we're talking about variance or deviation. So variance is a measure of the dispersion, which means spread, of data. For a binomial distribution, this value is found using this formula. So the variance of random variable x is n times p times q. We'll talk about what q is in just a moment. Standard deviation is found using this formula. So this is symbol for standard deviation equals the square root of variance. And that's the same thing we had when we did statistics. When we had a variance number, we take the square root of it to get the standard deviation. So we're going to do the same thing here. So now q, basically if your probability of success is p, q is your probability of failure. For example, if your probability of success was 0.6, then this probability would be 0.4. Right? Those two must combine to be 1. Alright, so let's try part A here. So with this coin flip again, we knew that's the binomial distribution as we had earlier. The variance can be found by multiplying these. So 8 trials, 0.5 for heads, 0.5 for not heads, or tails in other words. Multiply those. Variance is 2. And then standard deviation is square root of 2. Which is 1.41. So in other words, on average, we expect the number of heads we get to vary from the mean, which was 4, by 1.41. Okay, try B. In B, here's our binomial distribution, and our variance is this, which works out to this value, and standard deviation is that, which works out to this value. And the last one, okay, we have these workers going to work by public transport. Here's our binomial distribution, 15 trials, because we talked about 15 workers, and 80% of them go by public transport. Variance, expected value is this, which is 12. Variance is 2.4, and standard deviation is the square root of that, which is 1.55. Okay, here's another one. Take a look here. First, determine what is the probability that we get a square number. Think about what are square numbers, like 1 squared, 2 squared, and so on. How many of those 12 are square numbers? Okay, so square numbers are 1, 4, and 9 in these 12 possibilities. So that's 3 out of 12, which means 1/4. So our probability is binomial. We do 8 trials here, and 0.25 is the chance of getting a square number, because again, 3 out of 12. So that's our distribution. In A, we're looking for probability that S is greater than 2. That is the same as saying 1 minus probability that S is less than or equal to 2. Because if we're trying to get more than 2 square numbers, that means we're getting either 2, 3, 4, 5, that many square numbers. Sorry, not 2. This is greater than 2. That means it does not include 2. So we're looking for 3 square numbers, or 4, or 5, or 6 square numbers, and so on. So that means we're doing 1 minus the chance of getting 2 square numbers, 1 square number, or 0 square numbers, which is what this is. Subtract those, and you get that value here. And then expected value and variance using the formulas we just saw. Okay, read this longer problem here. Let's see if we can figure it out. Okay, first of all, expected values. So expected values for the one machine and expected value for the other machine. And we can say that on average, almost twice as many defective bulbs are predicted to appear in a sample of 6 than in a sample of 5. So this one we can see, yeah, the average is almost double that average, and that's the conclusion we can make there. Now looking at variance, here's a formula for the x variable, here's a formula for the y, and we can see the variances like that. And what that tells us is the spread of the defective bulbs, there's more spread for the first machine, right? We can see a bigger spread of defective bulbs. So basically there's more, you're going to see more defective bulbs. Okay, let's try this one. Okay, we're looking for probability that John is going to win more than 6 games. Our binomial distribution here is there are 10 games. Probability of winning is this, and we're looking for probability John wins more than 6. More than 6 is the same as saying 1 minus less than or equal to 6. Again, just like we saw in the previous one, more than 6 means 7 wins, 8 wins, 9 wins, or 10 wins. So then if we do 1 minus less than or equal to 6, 1 minus 6 wins, 5 wins, 4 wins, then we're left with the 7, 8, 9, 10 wins that we need here. Do this on your calculator using binomial distribution, and you will get your answer matching this. Now in B, we're looking for expected values, so we're going to use that formula, multiply, and we get the 5.5. Alright, I think this is the last one here. Give this one a try. Okay, so we're given the mean and the variance. Again, mean is expected value. So we're given expected value and variance, so that means it's a hint. We're going to use both formulas. So here's the expected value formula, or mean. So NP equals 7.2. We can't solve that. We have 2 variables. Well, let's make a formula for the variance. Variance is NP times Q, and remember Q is just 1 minus P. Right, so if we knew this probability would be 1 minus that one, right? If this was 0.8, then this would be 0.2. Okay, so there's our formula there. Now we have 2 equations, both have n and p as our variables. Since we have this system of equations with the same variables, we can combine them to solve. So for example, I know np is 7.2, so I'm going to replace this np here with 7.2 from here. Now I can multiply through here, 7.2 times 1, and 7.2 times negative p, which gives me this. Now I'm going to subtract negative 7.2 from this side, and I have negative 7.2 equals negative 4.3 once that has been subtracted. Finally, divide by negative 7.2, and we get p equals this. Now that we know p, we can put it in here to solve for n. N would be equal to 7.2 divided by p, right? So n equals 7.2 divided by the p value, and we get that value for n. Okay, great work. You're ready for the practice assignment. Let's get working on that.